Hello, friends. Good evening.
Hello,
Oh,
So nice to see you
good
after the
evening.
holidays. I hope you're full of energy to start our new course and you're refreshed. Your uh, your strength is much more, and I hope that you retained everything that we have studied during the probability course, so your brains are not empty after the holidays. Um, since we are already familiar to each other, I guess I can skip the introduction part. So you know me, I know you, and you. I hope you remember uh, my suggestion that everyone turns on the camera, such that I'm addressing the real people, the uh, not these black squares. Hi, Vladimir. Not your avatars or some strange pictures. So, guys, please, only two people who decided to do this, turn on your cameras, everyone. I can also reveal you one small, let's say, secret. While I'm grading you in the end of the course, and when there is some, let's say, doubt about your final results, or probably you're getting 4 or 5, there is something on the margin. And if I mentally remember the person, I mean the face and how the person looks like, you see that it works for your benefit. So that's why that's another reason probably to be present uh, on the lecture with your face. Okay, nice. So I told you a little bit about this course about statistics and what we are gonna do last time. So now more precise introduction into the course. So as usual, I'm still the PhD in finance and still PhD in economics at CERGI here in Prague. So let's remember what is the place of this subject in the whole curricula. So we passed probability. So I will tell you a little bit more about how the probability is related to statistics. So now here we have mathematical statistics, and in parallel we will have econometrics classes. So I will also briefly mention how we will organize these two subjects over this whole semester, because basically econometrics is based on the mathematical statistics, and we need to know something from mathematical statistics before starting econometrics. Then next year there is going to be econometrics too, so more extended version of the first econometrics. Grade is going to be exactly the same as for our last courses. Option 1, you do home assignments, you collect 100 points, and you pass without any need to go to the final exam. So many people have chosen this option last time and successfully passed exam without bothering with the final exam. Another option, midterm 40% plus final 60%. So I will announce about midterm well in advance. It's going to be somewhere in the middle, probably, well, end March, the beginning of April, somewhere there. So in the middle of, closer to 9th or 10th week of the semester. So course page, you're already enrolled to the course page. It's gonna be the same interaction on the Moodle with you. You will have all the materials published on this page. You will have all the exercises there. So now it is populated only with the books. So the books are gonna be exactly the same as we used for the probability course, because basically those books are about statistics, not about probability. And here I will place all the materials regarding the subject. So now they are hidden from you, because I will update this page over the semester. So with the books here, you can find the following thing. So this is something new. I decided to introduce it for this course. I created the constant meeting IDs for our lectures. So that's why you don't need to wait until my message in WhatsApp. So you can just use this meeting ID, and it's gonna be every Thursday lecture. It's gonna be the same. So no change in meeting ID. So you can just take this, or you can follow the link and add our Thursday lectures to your Tencent meeting software to the calendar. It's quite easy. So these 14 lectures would hold every Thursday, starting from today till 21st of April. Every Thursday, except for some force majeure, we will have these lectures. And then look, as I said, before starting econometrics, which is in your schedule on Friday, we need to build some knowledge in statistics. So that's why in the first 4 weeks of this semester, Fridays will be also devoted to statistics. So Thursday and Friday during the first 4 weeks of this semester, we will have only statistics. And then we will continue in a usual sense. Thursday is going to be statistics and Friday is going to be econometrics classes. So in the econometrics, I will tell you about this more. So don't forget about this, please. Tomorrow we will have another lecture of statistics. Because otherwise, there is no, let's say, reason to start econometrics, because we need to understand something from this subject before. So links and IDs are here. Please put them into your calendar. And as I said, you don't need to wait until my message in chat. Another thing that I'm gonna use over this course and over econometrics course is programming exercises, working with data. And here you can find the document that describes how you can install and set up Python software on your laptop. So please do this. I asked Klim, and he will do the same in the computer lab in the university. So if you are in Irkutsk and if you have an access to the computer lab, you can make the assignments there. But I think it's better to have it on your personal computer or on your laptop. So that's why please in the following days, this evening, tomorrow, over the weekend, install, so follow these instructions and install the Anaconda, which is the kind of the software framework for programming in Python. So later on, I will make, let's say, a gentle introduction into Python. So I will tell you how to work there, how to do the calculations, and then we will accumulate this knowledge more and more. And I hope you will develop some skills in this sphere. But well, this is very, let's say, highly recommended for statistics if you want to have a high grade outcome. And this is essential for econometrics, because in econometrics there is no other way of doing any calculations except for using some software. So there are different options. Basically, instead of Python, you can use R, you can use Stata, you can use SAS, whatever. But I guess the Python is more versatile, it's free, you don't need to pay for this. And it has much more other applications, so who knows what will be necessary for you in the future. So, as I said, recommended books are exactly the same as for the probability course, so that's why no need to introduce them once again. Yeah, so this is about organization. Any questions to me about it?
No question.
No question.
Okay, good. So this is some preliminary plan of the course. So that's what I plan to do with you over the next 14 weeks, over the next 18 lectures. So we will talk about sampling and statistics. What's that? We will introduce what is called large sample asymptotics, which is widely used nowadays in the statistics inference. We'll discuss something which is called sampling distribution, which is important to introduce the subsequent topics. And the subsequent topics are the interval and point estimation of population parameters. So basically, everything that we discussed in probability course, and we pretended to know the parameters of probability distributions. Now we will try to get these parameters with the help of the special techniques, which are called the estimation. So we will discuss what is called testing statistical hypothesis, highly important thing in every field when you apply statistics. It's not only about economics, finance, it's also about physics, chemistry, biology, whatever. So statistics is quite versatile thing. And then we will probably conclude the part of statistics with the topics of analysis of variance and categorical data. Then my very, how to say, optimistic plan is to introduce you to the machine learning. And because machine learning is somehow related to the statistics, those two fields are more or less connected. They definitely have some differences. That's why basically for this part there is no other way except for using some programming software. So of course some elements of machine learning are built on top of statistics and some elements are completely different. So I hope, depending on your let's say achievements in the programming, I hope that we will come to this point and we will try doing some machine learning stuff together with the real data. Yeah, now about the home assignments, how they are gonna look like. So my plan, this is initial plan, is to do the following. So you will still have something similar to what you had in statistics, small exercises. Now they're gonna be graded with 5 points and they're gonna be simpler. In most of the cases, you will not have some integrals, derivatives. In most of the cases, you will have just some arithmetics. Because in statistics, the most important thing is not mathematical part, but let's say the meaningful part. You need to understand what you are doing. So that's why in these small exercises, you will have some simple calculations and more of the comments and let's say some outcomes of how you can explain the things that you have calculated. And with the gentle introduction into Python, you will also get some real data analysis tasks that will be built on the Python programming. And so I hope you will gently master these skills. Don't worry. I mean, so most of these exercises are going to be very simple. You need just to repeat after me, just changing something in the code. So my plan is to give you some short tutorials on Python. So probably in the form of some short video, I will just demonstrate you, okay, go here, write here, put here, and then here you will see the result. Now try doing this with another data. But as I said, the first step, you need to install this software into your computer. So please do this in the following days. So this part I already explained. First 4 weeks we will have 2 lectures per week. Then we start econometrics, and then we proceed with 1 lecture per week only on Thursday. So this is our plan. Any questions here?
No.
I still see only 3 people, so others are hidden for me. Okay, good. So yesterday on the exercise session, you refreshed a little bit about the probability. So now let's move into the new field of statistics. So as I mentioned, in probability, we worked with some ideal objects and studied their properties. So what are those ideal objects? We pretended to know the random variables, their distributions. We listed a lot of different distributions: geometric, binomial, Bernoulli, hypergeometric, then continuous distributions, uniform, normal, exponential, and so on. We studied their properties, like pretending that we know everything about these objects. Those objects are ideal. Of course, they are the product of our mental work. It's not something real. So we also spoke about moments, mean, variance. We spoke about the joint behavior of random variables, how we can measure their dependency, and so on. So now we move to the real cases. So now we try to try to understand how we can use those models to describe the real world. Because of course, the real world is very complicated, and it's quite difficult to grasp, to capture all the features of the real world. But usually we pretend to use some models, and I hope you understood this idea from the microeconomics, for example. So when we abstract from something which is not important, and then we concentrate on the most important features of the behavior, let's say, of consumer, producer, firm, government, and so on. So the same thing is here. Now we want to choose, let's say, which of those models, which of those tools from probability is applicable when we want to solve some practical problems. Let's say, what is the probability that tomorrow you will get a loss from your stock investment? Because the stock investment is not known for you. So the price of the stock in the future, it is not known. It's to some extent it's random. So maybe we can predict the direction of the price. Maybe we can predict some behavior based on some other variables. We don't know, but still the precise price is kind of random. Or what is the expected loss per insurance company client in a car accident? You never know precisely. Would this happen or not? And if conditional on the accident happened, what is the expected loss that the insurance company needs to recover? Is there any relationship between a number of women in the corporate board of directors and the corporate profitability? Whether gender diversity affects the corporate profitability or not. These are just 3 examples of the real questions that we can pose, but in principle, all of these questions can be answered with the help of those tools that we discussed in the course of probability. So here we need to know the distribution of a stock price or stock return. Here we need to know the distribution or conditional distribution of the losses per car accident. This is also a random variable for us. Here we need to know the relationship, something like the covariance or correlation between one random variable, which is the number of women in the corporate board, and the other random variable, which is the corporate profitability. But the question is how, so like if we have these probability distributions, so how can we explain, how can we get the parameters of those distributions? And that's exactly the field of statistics. The statistics is designed in a way to help us to choose and to build those models that we discussed in probability. So that's why I was asking you always be patient, guys, with the probability. Yes, I admit this is a mathematics, but still we are on the way to the practical application. So now this is something that you need to understand. If you want to understand statistics, you need to understand this slide and the concept of this slide, because here I am trying to explain you what is going on. So in a typical statistical problem, we have a random variable x of interest. I mean, so the random variable that we are interested in. Stock return, car accident losses, corporate profitability, whatever you want. The distribution of this random variable is not known. So who can tell what is the probability distribution of stock return? Is this normal? Is this Poisson? Is this binomial? Whatever. Okay, so probably not binomial because the nature of stock return is not binomial. But what is it? Maybe neither of them. Maybe it is some other distribution. We don't know. And here we have two different, let's say, options, or two different extents of this problem. We completely do not know the probability density function or probability mass function. I mean, you even have no clue about the type of this distribution, what is the type of the distribution, binomial, Poisson, normal, uniform, whatever. Or let's say less problematic option is that the form is known. You know, for example, that this is a binomial distribution or exponential distribution, but you don't know the parameter theta, which describes the form of this distribution. So what is this parameter theta? This is the usual notation that we are gonna have in the whole course. So this unknown parameter may be a scalar or maybe a vector. So we may have several parameters that are not known. For example, I know that x has an exponential distribution. In the exponential distribution, there is a parameter lambda, and lambda is not known for me. I don't know what is this lambda exactly. You had exponential distribution yesterday in the exercise session. You know how this works. But in practice, if I believe that, for example, the losses are distributed exponentially, I don't know what is lambda for car accident. Or x has a binomial distribution, and the binomial distribution has two parameters, n and p. You also must remember from yesterday's exercise session what is binomial distribution. Well, okay, n is known. I can calculate how many outcomes I have, but p is not known. So what might be the binomial distribution in the case of these examples? Well, how many clients insured in my company will have the car accidents? You know, this is the binomial output, right? Because you either have a car accident or you don't have a car accident. And for example, if there are 10,000 clients insured in your company, so you know N, but you don't know P, you don't know the probability that the car accident would happen. What is P? 5%, 1%, 10%, you don't know. Suppose X has a normal distribution, you know the form of distribution, right? With some mean and variance. Both mean and variance are not known. Well, if we believe that the corporate profitability has a normal distribution, but what is mu? What is sigma? Who knows? So that's a typical statistical problem. We believe that some variable is random. We believe that, and we know that every random variable must have a probability distribution, either in the form of PDF or PMF, doesn't matter. But then the problem is that we don't know how to describe this distribution because we don't know the crucial parameters. And so this is the crucial terminology that we will use throughout the whole statistics course and econometrics course. So this theta is called a population parameter. So in this case, population parameter is lambda, in this case is p, in this case is mu and sigma. So here theta is a vector because it has two parameters to be estimated. And in general, we denote the unknown population parameter as theta here. And we need to estimate it. So this is the process that we will be using over the whole course. So we will say that the random variable x has a density or mass function dependent on the nature, whether it's continuous or discrete variable, of the form f of x and theta, or p of x and theta, so where x is just the value of this random variable and theta is unknown parameter. So theta must belong to some set of omega, and this set of omega is a set of possible values of theta. So for example, here p cannot be less than 0 and greater than 1, right? So that's omega. So the set of possible values for an unknown parameter. So lambda in the exponential distribution can be positive. Sigma for the normal distribution can be also only positive number. So that's exactly what this set omega means. So just we need to understand what are the possible values of theta. Okay, so now in the more formal way regarding the population and parameters. So when we speak about the population, we speak about a large body of existing or conceptual data, including all available objects or observations of a random variable. So it might be existing, it might be conceptual. So what is the difference? So existing means that you are talking about the population of objects that exactly exist. For example, you want to calculate what is the average age of people in Russia. So the population for you is going to be the total population of the country, like 140 something million people, each and every person living in the country. That's going to be the population. Conceptual data means that you do not have this object existing. For example, the losses from the car accident. So you don't have all possible outcomes from the car accidents present, and you cannot see them in reality, like people living in the country, right? So you just conceptually think, well, the loss in the car accident can assume values from 0 rubles to, I don't know, 5 million rubles, depending on the price of this car. But in practice, you never observe all of them, and they do not exist. So that's a conceptual data. So the example of population parameters. So the parameters of PDF or PMF, like lambda for exponential distribution or Poisson distribution. So those are population parameters. Or population mean, which is the expected value of a random variable. You know this. Or the population variance, sigma squared. Or the population quantiles. You also mentioned quantiles yesterday on the exercise session. So the such value of the random variable that kind of gives us the exact probability. So why we can be interested in the population mean in particular? That's an interesting thing, because we will start our discussion of the estimation and statistics, and we will proceed mostly with the calculation of the estimation of the population mean. Now there is a justification why we are so concerned, we would be so concerned with the population mean. So first of all, if we have a binomial distribution and we want to calculate the expected value of x, which is mean of x, and this is NP. So you see that population mean depends on these two population parameters. And knowing n and knowing mu, we can easily infer about p. We can easily say what is p. If x, for example, is distributed with the Poisson distribution, and lambda is the only parameter of Poisson distribution, then the expected value of x is just lambda. Again, so population mean is equal to the unknown parameter of this population. If x is distributed exponentially with the parameter lambda, then the population mean is 1 over lambda. Again, if you know the population mean, you can calculate what is lambda, what is the unknown population parameter. So in the normal distribution, so mean itself is the parameter that forms the shape of this distribution, the center of the distribution. So that's why we will start our discussion of statistics and estimation procedure with the population mean, because the population mean is kind of widely used in, and it has a relationship to many to the parameters of many important distributions. So now we pose the problem. We want to know something about the probability distribution of a random variable, and this probability distribution is not known for us. So we want to understand what is the applicable probability distribution for one of those practical cases that I described: stock return, car accident losses, corporate profitability, whatever. So how we can do this? So this is the first and the most important step. If you do this wrongly, I mean in practice, it would fail the whole thing. The first step is random sampling. So the information about this unknown distribution or parameters of distribution of this random variable of interest can be obtained from a sample derived on this random variable. So what is sample and how this is related to our goal? So the sample, we need to observe this random variable in practice. We need to observe the outcomes of this random variable in practice. And these sample observations will have the same distribution as this unknown random variable. So we denote the sample observations as the random variables x1, x2, this is a typo, must be xn, where n denotes the sample size. Look, before drawing the sample, before collecting the observations of the sample, the values are not known for us. So therefore, we think that we treat the outcome in each repetition or in each sampling step as the random variable. But once the sample is drawn, when the sample is actually drawn, we will denote the values collected through the sampling with the lowercase letters x1, x2, and xn. And we will call them realizations of the sample. In the next discussion, in this lecture and all the following lectures, we usually will assume that the sample observations are mutually independent. So this is crucially important, and independency, we discussed what is independency. So basically when the joint distribution of these variables is just a product of their individual distributions. And here comes the definition. So if the random variables x1, x2, etc., xn are independent and identically distributed, or just to short IID, and you will see this IID acronym throughout the whole course of statistics and econometrics, then these random variables constitute a random sample of size n from the common distribution. Wait a second. Yeah, okay, so for example, just to understand what's going on here. If you want to know, let's say the average age, or let's say if you want to know the distribution of age of citizens of Russia, let's say this is our population. So X is a random variable, which is age. Now, what would you do? You will ask people about their age, I don't know, talking to people on the street. Before asking the person, imagine that you have some blind on your eyes, you don't see the person, and you cannot just, you cannot infer, you cannot guess the age by the appearance of the person, right? So you don't see the person, or you just call the phone and you ask the person about the age. So before asking, you treat the age of every person that you ask. So imagine that you will ask 10 people about their age. Before asking them, the final result is not known for you. So therefore, this is the random variable for you. So that's x1, x2, x3, and so on. So those are suggested responses of people to your question, what is your age? Okay. Once they responded, so suppose that the first person said, well, I am 22, another person said, I am 56, and the third person said, I am 18, and so on. You know the realizations of every single repetition in your sampling. So this is going to be this lowercase axis. 22, 56, 18, and so on. So in this sense, the age is random variable. It's not like a random variable for the person who knows the age precisely. It's for you as a researcher who does not know the value, the outcome in advance. This is going to be the random variable. But once you asked, this is just a number, which we call realization. Is this clear, guys? What we are talking about? What is a random sample? What these x1, x2, and so on mean? And these lowercase letters.
Pretty much.
We lost some people, I guess. So maybe
Немногие вернулись с поля.
yeah, maybe I somehow frightened them with Python programming or whatever. I mean, even from the beginning of the lecture, we lost some people. Okay. So the simplest possible way, practical way, how you can draw this random sample is called simple random sampling. So if uppercase n and lowercase n represent the number of elements in the population n sample. So for example, uppercase n is the total number of people living in the country, 145 million people. And lowercase n is the number of sample that you draw. Well, 10 people. You ask 10 random people about their age. So this is crucial and important thing. If each particular sample of size n has the same probability of occurrence in each of these possible samples, because look, now we are talking something about the about what? So do you remember the part about the counting? So that was the third lecture in probability. So look, when we have the total population of n and we randomly select n lowercase n elements from this population. So what it is gonna be? How the process is called? When I want to calculate how many possible outcomes I can have. Do you remember? So for example, there are how many? There are 18 people now present on the lecture.
Combination.
Yes, we are talking about combinations, right? Because we are not, we do not care about their particular order, right? So I don't care who is the first person, who is the second person, who is the third person. I just care about the composition of this sample. Yes. Okay, so this is the number of possible samples, and if each sample is equally likely to appear, then we talk about simple random sampling. Look, practically this is very difficult to achieve, because practically it means that it is equally likely to ask about the age of the person living somewhere on the seashore in the far north, close, I don't know, close to the Bering Sea, and the person on the Red Square in Moscow, and the person, I don't know, living in Kaliningrad, and the person who lives on the spaceship International Space Station, let's say. So the probability that you would ask each of this person is gonna be the same. You see that practically it's very difficult to achieve, because practically, well, at least if the person lives in the town, has some telephone, and probably walks on the street, is much likely to that this person is going to be asked by the questionnaire, by the interviewer about the age. But conceptually, we believe that when we work with a sample, the probability that every element of this sample appears, every element of the population appears in our sample is the same. This is quite important thing, because we want to lay down the mathematical framework and mathematical justification for the subsequent derivation. So that's why I'm kind of stressing these things. So generally, sampling without replacement induces dependence among X, because if you drew the person, if you call this person or talk to the person once, then the probability that you will ask another person is going to be slightly higher. So for example, look, if I randomly select one of you, the probability that I will select one person among 18 of you is 1 over 18. Once I selected this person, without replacing this person back, the probability to pick another person is going to be 1 over 17, which is the higher probability. The probability to select the third person is going to be 1 over 16, and so on. So the sampling without replacement induces dependence among the random variables because it somehow shifts the probability, which contradicts the previous idea that we want the variables to be independently and identically distributed. So how we can kill this problem? We assume that the sample size n is very small relative to the population size large N or capital N. And then in this case, we can think of that a simple random sampling produces the IID variables. So look, if we have the total population of the country, 145 million, and then I select, let's say, 1,000 people. So practically, the probability that I will select 995th people is not very much different from probability of selecting the first person, right? It's going to be the same because the difference is quite small. But once my population is very small and the sample size relative to the population size is comparable, then we are in trouble. But we will not talk about these things. So usually in statistics, we assume this. And another thing, which is kind of discussable, so just, for the future to understand. I think you've heard about big data thing, right? So big data, when we have nowadays nice computational capacity, very powerful computers, and people or researchers, they really prefer to work with the large samples of data. So I've read several articles that actually claim that once you are collecting a lot of observations, so n is large, and it kind of comes closer and closer to the population size, you may destroy the credibility of your calculations. So not always working with the big data is better than working with small samples. That's kind of the controversial thing. But definitely we need to understand this, so we will not go into this field. Just we need to understand that everything comes at a cost. So examples, as I said, sample of 1,000 respondents from a population of 100 million people. So this might be thought as the simple random sampling producing independent and identically distributed variables. Why? Because the sample size is relatively small to the population, or a sample of 100 firms from a population of 1 million firms. Something like this. So now, the course is called statistics. So statistics is a field, statistics is maybe we can say it, science, a discipline. But actually in statistics, we are studying something which is called statistic. So what is this statistic? Once we draw a random sample, so the sample on a random variable x, and we have some function. So large T is just a function on these random variables. And then we call this function as statistic. So everything that is based on the sample, on the random sample, is going to be called a statistic. When we actually collect the data on a sample, then small t or lowercase t is gonna represent the realization of this statistic, and it's gonna be the same function, but the function calculated based on the realizations of these random variables. So each observation is a realization of IID random variables. And as I said, a statistic is a function of the observable random variables in a sample. And now here comes an important thing. Every statistic is a random variable itself. Why? Because it is based on the random variables. So this is the function of random variables. And in statistics, good news, we are gonna be interested in the distributions of these special things, of the special random variables. A statistic has its own distribution, and every statistic has something which is called a sampling distribution. And how it is related to the practical problem that we posed in the beginning. So now, when we have a random sample, and we believe that the random variable of interest that produces this sample has some probability function, probability density or probability mass function with an unknown parameter, then we can use a statistic, we can use a special function t to estimate this unknown parameter theta. So this is another important thing just to understand. We usually use something which is in the population and unknown with the Greek letters. So that's why we have Greek theta here. And we are gonna use the Latin letters like T, which is the counterpart of theta in Greek, to represent their sample analogs or sample counterparties. So this statistic, this function, which is based on the sample, on the random sample, is an estimator of theta. More formally, it's going to be called the point estimator. We will discuss the theory of point estimators and the practical issues of the point estimation maybe in the third, fourth lecture. And the realization of this estimator is called an estimate of theta. Once again, this is just an introduction of the terminology, and this terminology is going to be used every time that we calculate something and every time that we want to make some inferences about the probability distributions. So, as I said, we will discuss the estimators and how to construct them in the next lectures. So we will have at least 3 lectures on the estimators. So now there is an example, practical example to understand all these issues and all the concepts that we have discussed before. So assume you are interested in the mean salary of a working population in Russia in January 2022. So we have a population of interest, which is just the working people, those who work. And you want to know what is the center of this, of the distribution of this variable, right? So what is the mean salary? So what is the population? All people who work and receive some salary. And basically, if the person works but receives 0, it also counts. How large is this? So, can you guess how large is the population?
146 million. something like that.
Working population. I
100
believe not
Ah.
everyone works, right? In
50%,
Russia.
like 67 millions, maybe.
Something like a half, but actually we don't know, and nobody knows. I will kind of I will reveal you this truth. Why? Because it's practically almost impossible to understand kind of know exactly how many people work in the country. We can just estimate this. We can guess, let's around this number. But practically, today a person works, tomorrow this person is fired, and several people found their job. So every day, every minute, this number changes. That's why it's practically not possible to collect the data on the whole population. You start asking people about their salary. Tomorrow, part of these people will lose their jobs, and other people will find a job, and your work is going to be very, very hard if you want to calculate the mean salary of the whole population. So what is the practical solution of this problem? We need to collect the random sample of working people. Now the question is, just try to suggest how would you collect this random sample if you believe and if you remember that the sample must be so the procedure must be this simple random sampling, which means that the probability to appear in your sample for every working person is going to be the same. So how would you collect the data on the salaries practically? Suppose you want to know the salary of 1,000 people. How would you find these 1,000 people in order to collect truly random sample?
We can ask them on the streets, I guess.
Okay, on the streets. On which streets?
Central streets, or maybe somehow like in the different streets in the poor regions of the town and in the rich regions of the town, stuff like that.
Of which town?
Of a capital? No, not in the capital. Okay, I don't know.
You see that practically this is very difficult, because the probability of a person who lives in a faraway village in Chukotka and does not go on the street must be the same as the probability to ask, for example, Roman Abramovich. Must be exactly the same, and Roman Abramovich doesn't walk on the street, but the probability must be the same. As I said, this is very difficult to achieve. Nowadays, as I know, many such surveys are run with the telephone calls. So maybe this is more or less fair thing, because you randomly call a person, you do not know who is this person. You can ask, do you work? If the person responds no, okay, so you just say, thank you, sorry for bothering you, and then you call to another person. Another problem, you wanted to ask people on the streets, but working people probably do not walk on the street, right? So they work. So that's why the probability that you would ask unemployed person, or maybe student, or maybe the retired person is higher than when you ask the person on the street. When you call the phone, Another problem would be that probably not all the working people can respond the phone calls during their working hours. Even if you call them in the weekend, they are probably gonna be pissed off with your telephone calls during the weekend mornings with such strange questions. So everything that I'm explaining to you just needs, you need to understand how practically it is difficult to collect a truly random sample. Some procedures are closer to this random sample, and if you collect like the data for 1,000 people, that's gonna be okay. I mean, this problem is gonna be negligible. But as I said, and I asked in which town you want to ask these people, because if you ask people only in your hometown, then the population is going to be the working population of your hometown. It's going to be not the truly random sample of the working population in the whole country. Maybe the time of your questions must be different today, tomorrow, 1 week after, and so on, because as I said, the working population differs. That's a problem. That's a real problem. We are not gonna discuss the designs of this random sampling, definitely, but just keep this in mind that every time when you work with the data, first of all, you need to critically evaluate this data, whether you can treat this data as a random or not. If this data appeared because you asked your friends, probably this data is not random. Most probably. So now, before you ask a person, like 1, 2, 3, first, second, third person, and so on, 1,000th person, before you ask a person about the salary, this number is not known to you. So that's why before asking, you have a random variable. So the salary of the first person, the salary of the second person is going to be random. And here, another important thing, when you start asking people on the streets, and if, assume that we ask people near the business centers, and we ask other people near some working areas of the, or industrial areas of the city, would these random variables be identically distributed? Probably no, because you may believe that the salary of people who are kind of walking near the business centers on average is higher than the salary of people who are walking near some industrial areas of the city. That's another issue. So as I said, if you start asking people in Moscow only, then the salary in Moscow is not identically distributed as the salary of people living in Chukotka. They're different. That's why the probability that you ask the person from Chukotka and the person from Moscow must be the same. And you, before asking, actually don't need to know where this person lives. That's why probably the phone call is better, when you randomly call a person and you don't know the location of this person. After the person responded, after you call and the person said, well, my salary is 70,000. Another person said, my salary is 100,000. The third person said, my salary is 20,000, so on. You have realizations of these random variables. Now they are no more random, they're just numbers for you. You have these numbers, you can work with these numbers. Is this example clear?
Yes.
Only for Vladimir? Or for other people?
I guess there are just two of us now.
Okay. So now we move to one particular example of a statistic, which is going to be used everywhere. This particular example of a statistic is called a sample mean. So if we have a random sample of independently and analytically distributed variables from x1 to xn, every variable in this sample has the same mean, which is denoted with mu, and the same variance, which is denoted with sigma, then the sample mean is defined as a simple arithmetic average, 1 over n multiplied by the sum of these random variables. This is a sample mean, just simple arithmetic average. Since these variables are random, and we said that every function of random variables is itself random, the sample mean is also a random variable. So can you guess what is going to be the sample mean or the arithmetic average of the responses to your question about the salary from 1,000 people before asking them? No, you don't know the answers of these people, and you don't know what's going to be the arithmetic average of their responses. So that's why before asking, this is a random variable as well. And we will call the probability distribution of this random variable the sampling distribution of a sample mean. And we are going to be particularly interested in this distribution. So we will want to build to know as much as we can about the distribution of this random variable. So moreover, the sample mean is an estimator of the population mean. So later, when we will discuss the estimation procedures, we will justify why sample mean as an estimator of the population mean. Now, just believe me that this is an estimator as well. The sampling distribution of sample mean determines how accurately this sample mean estimates the population mean. Population mean is unknown for us, and we want to guess this population mean, and that's why we collect a sample and we calculate the sample mean. And before doing this, we want to build some nice theory about this. We want to understand the behavior of this random variable. And of course, the more tightly this sampling distribution is centered on this mu, the better the sample mean estimates the population mean. Because then the interval where this population mean can be contained is much more narrow. So this is just some recap from the probability, just to remind you, because we will need this now to build something about the sample means. So recap from the probability. When we have the random variables x from 1 to n and y from 1 to m, we have some mean for these random variables and some mean for these random variables, so mu I for x and xi j for y, and we define the linear combination of these random variables. So u1 is the linear combination of x's, u2 is the linear combination of y's. A and B are just some constants, and then we derived in probability course the following relations. So the expectation of this linear combination of these random variables is just the sum of expectations of x's multiplied by these constants. The variance of these linear combinations is the sum of variances of x squared plus 2 multiplied by the covariances of xi and xj. That's basically what we would need. So I will skip the third part. This is not necessary for us. Just concentrate on these two parts. So why we want to know this, why we want to remember this? Because once the sample mean is the random variable, we want to know the sampling distribution of the sample mean. And well, here is the way how we can get it. So the expectation of this random variable is going to be also mu, so the same as the mean for each of these variables. And the variance of sample distribution is sample mean, sorry, is sigma squared, so the variance of one of these realizations divided by n. How can we prove this? Easy, from the previous slide. What is the sample mean? Sample mean is the linear combination of random variables from 1 to n with this expectation. Okay, so we have this. So let me go back here. So ai is 1 over n every time. Xi is this, right? So 1, 2, 3, 4, and so on. So now the coefficient moves out of the expectation sign because the constant, the expectation of the constant is just a constant. The expectation of the sum, what's that? Again, based on the previous slide, this is just the sum of the expectations of x. Now, what is the expectation of xi? Well, this is mu. For every x, the expectation is mu. So therefore, we have n of these mu's divided by n. Finally, we have the expectation of the sample mean, which is also mu. Variance, same idea. First of all, we put here the way how we calculate this sample average, or sample mean. Then this coefficient 1 over n goes out of the variance squared. And now very important thing, look, when we calculate the variance of a linear combination, these covariances must appear. But if the variables are independent, covariance for independent variables is 0. So that's why this part with covariances just drops and we have the summation of variances. This is why we are so concerned with this IID. We want to have independently distributed random variables because in this case, the sample mean has very nice distribution and the variance of the sample mean might be calculated in a very nice way. So it's just the sum of variances of every x, and since every x is identically distributed with the same variance, we have finally this sigma squared over n. What it suggests. So ideally we want to know the PDF or PMF of the sampling distribution, not only these two moments, but practically we cannot determine the sampling distribution if we do not know the population distribution function, and we don't know the population distribution function. Look, we just say that they are IID and we don't care about the distribution of these variables. This is actually a very important thing also. So it doesn't matter what is the distribution of this axis, what is the distribution of these variables. This relationship holds always. We will study the approximation of the sampling distribution of the sample mean in the next lecture. Now, since we don't know neither mu nor sigma squared, but we now have a way how we can estimate mu, because the estimator of mu is x bar, sample mean. Now the question is how we can estimate the population variance. And there is another statistic and another estimator, which is called the sample variance. So the sample variance is defined in the following way. So we need to sum the squared deviation of every sample variable in the sample from its sample mean, squared it, and then divide this by n minus 1. So this is a very important thing. So it's not divided by n, this is divided by n minus 1. And this is called the sample variance. Why n minus 1? We will discuss a little bit later. So now just believe me that the sample variance must look like this. So another thing is the same. Since these are the random variables, their combination is also a random variable, and it also has some special distribution, but we will discuss this distribution probably in the third lecture. So, and sample variance is one of the population variance estimators. There are many. So we can estimate the population variance in different ways, and the sample variance is one of them, which has nice features, nice properties. So we will discuss the other estimators in the future, lecture 4, 5. So now I want to show you basically that's it with the introduction into statistics and sampling. So we spoke today about two types of statistics: sample mean, sample variance. So now I want to show you how this works. Why are we talking about this? So suppose, once again, everything now is going to be built with the help of ideal models. Suppose that we know everything, because it gives us some, let's say, sense of understanding of the whole thing. So suppose that we have a die and we toss this 3 times. Of course, I don't have like practically this, we will do this mentally, right? So denote x1, x2, and x3 the number of spots observed on the upper face for the tosses 1, 2, and 3 respectively. So you have a die, you throw this, you have, let's say, 2. But before throwing this, x1 is the outcome that is going to be on the first toss, x2 is going to be on the second, x3 on the third. So suppose we are interested in their average. So suppose that we are interested in the average of these 3, which is the sample mean. The average number of spots observed in the sample of size 3. Look, before throwing a die, I don't know what is going to be x1, what is going to be x2, and what is going to be x3. Therefore, this is also random for me. I don't know what will be the average of 3 tosses of a die. So I want to know what is the mean of this average value, what is the variance of this average value, and ideally what is the distribution of this average value. Thankfully, the case is such that I can build the whole distribution of it. That's a question. Practically, once again, when we speak about stock returns, when we speak about car accident losses, when we speak about salaries, whatever, we do not know what is the probability of this, x1, x2, x3. But in this toy example, we know everything. We know what is the distribution, right? We spoke about this in the probability course. So what do we know? We know that for every repetition, xi, has a discrete uniform distribution where probability to obtain one of these 6 numbers is 1 over 6. We know this. Probability to observe something else is 0. Okay. So what is the expected value of a number of spots on one toss of a die? This is 3.5, right? So we just need to calculate this as the usual expected value. I hope you remember how to calculate expected values. Just 3 weeks passed from the probability course. So you take one realization multiplied by probability, second realization multiplied by probability, and so on. That's 3.5. What is the variance of this random variable? This is 1 squared times probability 2 squared times probability 6 squared times probability minus the expectation squared, right? So this is the more appropriate, let's say, way to calculate, and the variance is going to be this 2.9167. Now, x bar, so the arithmetic average of these outcomes. What is the mean and variance of this random variable? So it's going to be 3.5 as an expectation. So we proved this in the previous slide. And the variance is going to be 0.9622. So the variance of sample average is lower than the variance of every outcome here, which is quite reasonable, I guess. So in this case, can we derive the whole distribution of x bar? Yes, we can, because we know the distribution of single x's that are included into the sample mean. So in order to do this, we need to enumerate all possible outcomes in our experiment. So now, what are these possible outcomes? There are actually 216 distinct outcomes for every sample. And here are just several examples. So we can get 1, 1, and 1 in all 3 tosses of a die. So this is one particular outcome that leads to the average 1. And the probability to get sample mean equals 1 is 1 over 216. So probability to get 4 over 3 as the sample mean can be obtained in 3 possible options. 2, 1, 1, 1, 2, 1, 1, 1, 2, right? So which is 3 over 216, and so on. I mean, so you need to enumerate all possible outcomes. There are 216 of them, and all possible outcomes of this arithmetic mean. So that's what you will do. Now let me demonstrate you what we practically have, because now everything here is constructed in our mind. So now what practically we have, if, for example, you are concerned with something which is more, how to say, more advanced, not just rolling a die. So imagine the following experiment. You take a die, throw it 3 times, and record the realizations, x1, x2, x3, and calculate their average value. So how it will look like in practice? So let me demonstrate you. So let's say we have a sample 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 times we repeat this experiment. And here is going to be die 1, die 2, and die 3. So our sample size is 3. Here is going to be an average, or the average of these 3 outcomes. What will be, so let me just simulate, instead of throwing the real die, let me just simulate this with the following function in Excel, which is called run between. This is exactly the uniform distribution, the uniformly distributed random variable, and you just set the upper and lower limit for this. So look, first die will give you 4, second die will give you 3, third die will give you 1. What's the average? I just sum over them, this plus this plus this, divided by 3. Okay, here is an average. So now let's say I repeat this experiment again and again and again. So second time, third time, fourth time, and so on to 10 times. So you see that every time I'm getting different average. So here's the average is 3.7, here is 2.3, here is 3.7, here is 3, and so on. As I said, upon the experiment, before the experiment, you do not know the realization. But after the experiment, this is just a single realization of the random variable. And every time you repeat your experiment, the realization changes. That's a crucial thing. So what is the variance of this average? So I can just use the function to calculate the variance. The variance of this, let's say 0.72, but it also changes, look, because this sample variance is itself the random variable. Basically, here's sample variance of these three things. And you see that for each sample, the realization of the variance is different. And the variance of mean is also different. That's what we have. Once you collect the data, let's say so keep thinking about the problem about the salary. Once you collected the sample of 1,000 responses from people, this is just one line here, and you will have one particular average and you will have one particular variance. But you must be conscious that if you draw another sample with another people responded to you, you would have another average and you would have another variance, which is very important thing to understand the whole concept of statistics, because based on one sample, we want to infer about the population parameters. And we will build such tools. How can we, based on this one particular sample, infer about the population mean? Because now look, if you throw these 3 dice once and you will get the average of 4, you will miss the true expectation, which is 3.5. You see that the realization is 4, the expectation is 3.5. Your target is 3.5, but you missed and you shoot to 4. With another sample, with the second sample, you miss your target even more because it's 5.3 instead of 3.5. You see, once you collect the sample and once you calculated something based on this sample, the realization might be pretty far away from your target. So that's the way that we are gonna explore in statistics. We are gonna explore, based on the sample, how far or how might be our calculation or our estimation, how it might be far from the true target that we don't know. Our problem is even worse, because now we know that the true target is 3.5. I can compare my realization with the target. I can say, well, this is too far from my target. This is very close to my target. In practice, we don't know even the target, where it is. Okay, so that's just another way to explain what I was talking to you right now. Yeah, the realization. You must see, not we. Okay, so to conclude, what we must get from this lecture. So usually the parameters of random variable distributions are not known in many practical applications. The essence of statistics is to infer about these parameters based on the random sample of the random variable of interest. Once we calculate something based on this random sample, which is called statistic, it is itself random. And we want to know the properties of these statistics, how they are, let's say, good in estimating the population parameters. Well, we can estimate the population mean and variance. I showed you how, and now the next question is how to capture the idea about the probability distribution as a whole. Is it possible or not? So that's going to be in the next lecture tomorrow. Questions?
I have no questions personally.
No questions.
Vlad, you seem tired.
No
Yes,
questions.
it is almost 7 p.m. in Irkutsk. So yes,
But it's the
we are
first day of
tired.
statistics. You, as I said, you must be energetic. So if you will continue being tired over the semester, it's not that good.
We hope our schedule will be changed soon. So yes.
So other people.
No.
Okay, then see you tomorrow. Grab a cup of coffee and find some other ways how you can keep your energy. So we need this energy for this semester. Bye,
If we
guys. See you
drink
tomorrow.
coffee, if you drink coffee at 7 p.m., we will not be able to sleep.
That's nice. You will have time to install Python, to do homeworks, so on. See you guys tomorrow.
Goodbye. Thank you for the lesson.